Hello, we're going to talk about 10.5, the normal distribution, and it says here that the normal distribution is the most important continuous theoretical probability distribution. And that's true. There's a lot of things in life that are modeled by the normal distribution. So we'll go over those in a little bit, but for right now, the PDF, the probability density function of the normal distribution is f of x, where it's 1 over sigma times the square root of 2 pi. Now remember, sigma, sigma squared is our variance of a distribution. Minus x minus our mean, all squared, all over 2 times sigma squared, which that is our variance, and where x is in the element of the real numbers. Now, this might seem really complicated, and it is, but we're going to end up not using this quite too often, actually very little from the top of my head, but we'll see in the future. So, so the way that we define it and talk about it, just like we did in the binomial distribution, if f of x depends on we have parameters mean and sigma, right? Then the random variable x described by the PDF is a normal variable that follows a normal distribution with mean and variance sigma squared. Rewrite this as x follows a normal, and then our parameters will put our mean, and then we'll put our variance in here. So we're going to use this notation when we're talking about this. Now, some properties of the normal curve is it is a smooth bell-shaped graph, right? It is a bell-shaped graph. It is symmetrical about the vertical line x equals mu, which is our mean, and has a maximum point at x equals mu, so it comes up to a maximum. It has a horizontal asymptote on the x-axis, and has 2 inflection points, right? So it changes from concave up to concave down, from where x is equal to mu plus the sigma, and the sigma, and then, or this could be called the standard deviation, or minus the standard deviation, right? So, and here's an example of what it looks like right here. So this is a bell-shaped curve. So you're going to have a maximum point right here, right? And then you're going to have an inflection point. Kind of looks like right at about 1. So this one almost looks like it has a standard deviation of 1, and it changes from concave down to concave up right there. So what I want to do now, let's look at what it could look like on the calculator to see what happens here. So, and we can use the calculator as such. So let's go ahead and look at this one. So I'm going to go on, and I am going to define my variable as a normal distribution. I'm not going to use this formula. I can actually use the calculator to help me. So I could say f of, well, let's do this so you can see what's going on here. Why can't I see it? There we go. That looks a little bit better. Not quite that bad. There we go. So I'm going to define my function f of x. I mean, I could type in everything that is the normal distribution here, but we can actually have a function for that. So I'll go menu, probability, distributions, and you can do make sure you do the normal PDF, because this is a PDF, not the CDF. And we're going to have a random variable x. And this here is where we're going to have, it has your mean 0, so that's where you're centered. Your mean is centered right at the, on the y-axis, right, where x equals 0, so that's your mean, and a standard and a standard deviation of 1. And this is also called the standard normal distribution. So just a standard normal distribution with mean 0 and sigma, or standard deviation 1. So I'll go there. And now I've defined it. Now I'm going to define 2 more, or 3 more actually. So I'll go, this time I'll keep the mean 0, but I'll make this 2, and I'll change this letter. So I got f, then I'll have g, so I've defined that one, and then I'll make another one with another, I'll make that 3, and I'll make, so I got fg, and then h right there, and now I'll go and I'll change this one, I'll make this a standard deviation of 4, and then I'll make this one p, right? right here, and then I can go insert a page, and I want a graph, and then I can put in my first one I put in was f of x, and it gives me this. It's kind of hard to see, so I'm going to go menu, window, and I'll do fit A, and it'll fit it right on the graph there, and then that is a standard. This is a standard normal, right, where it has mean 0 right here, symmetric about it, and then it's points of inflection are one from the mean, right, plus or minus, and it changes from concave down to concave up there. But let's go ahead and put in the other ones. So I had f, I had g of x, and you can see what happened, right? It's the more standard deviation, it gets more spread out, and then I can put in the h of x. And it gets more spread out because that was the standard deviation of 3, and then the last one that I had was p of x. And it gets even more spread out, as you can see. And there you go. So let's look at a couple other problems that we can see using the standard deviation. Before we do that, just I wanted to go over real quick. So first, normal variables include, under certain strict conditions, height, weight, and age. Those usually tend to follow a normal distribution. Mass and volume of a lot of things are normal. Time taken to complete an activity, right? You know, and scores of test exam, absolutely. Our scores almost always follow. That's probably a pretty big one there, right there. And those are scores on tests, depending on how many people it takes, usually going to follow a normal distribution. And then random errors in experiments or process. Those are all examples. How do we calculate the normal distribution? Right? Well, it's just the same as we've done before, right? And it's going to be the integral from a to b of f of x d of x, and we can find the probability in between those units, right? And then we'd find its antiderivative. But the good thing is, for these ones, I'm sure you'd be satisfied, this type of here, when you have e to, it's going to end up being an x variable squared. This one has there's no way you can do this by hand. You have to, so we're going to end up using the calculator for these most of the time. So the first time, first question it asks us here is example 28. It says, state given reasons whether or not each of the graphs could not be a normal curve. For the first one here, this should be for any, continuous random variable. We know this f of x has to be greater than 0. And so this one, the reason that this one is not a normal distribution or any distribution, any continuous, is because it's below 0. That can't happen. And we talked about, we saw the graphs of the normals. They only come up to one maximum point. This could be a distribution, but it's definitely not a normal distribution. But this one is, you can tell this one definitely follows a normal distribution. And it looks like a standard normal. It looks like it's got a standard deviation of 1. So that might be the standard normal distribution right there. Good? And then next problem we're going to look at is it gives us this. It says given that x follows a normal distribution with mean 3 and 2 squared as our variance, calculate p between 1 and 3. So just going to use the calculator on this one because we cannot integrate the standard normal. So let's do this. So what I'm going to do is, if I'm going to find these values between 1 and 3, I'm going to go menu, probability distribution. Now, since I'm doing the area between this, I'm going to need my CDF, not my PDF, right? So I'm going to use my CDF right here. And I need to go, a lower bound would be 1. Upper bound would be 3. And in this situation, I have a mean of 3. And even though in our notation we use the notation variance, here they only want the standard deviation, and standard deviation is 2. And then I'm going to go OK and get my answer. So the probability that 1 is less than x is less than 3, that's going to be 0.3413. Good? And then the next one I'm going to look at gives us two options here. It says x follows a normal distribution with mean 3, and it's pretty much the same type of normal distribution, right? this time it's probably is less than 2, right? So menu, probability 5, distribution 5. I make sure I do a CDF, not a PDF. Now, since it's less than 2, it's going to start all the way. If you remember the normal distribution, it goes on forever. It's a bad graph. Normal distribution goes on forever, right? So I just want a really small number, which it already is on there, right? But then my upper bound's going to stop at 2 in this one, so I'm going to go to 2, and then my mean was 3, and my standard deviation was 2, right? So I go like this. So my probability that x is less than 2 is going to be 0.3085 approximately, right? Now this time it asks us for probability x is greater than 4, right? Well, I could copy this one too, but I'm going to start at 4 right here, and I'll not a negative, so I'll start at 4, and then here is my upper bound. I already have this loaded in with the proper mean and standard deviation. I just want to, but I need to go for an infinite. I can't put an infinity in there. I have to put a number, but I'm just going to put a really large number. One I like to choose is 10 to the 10. That's a huge number. You usually get a pretty accurate answer when I do that number. So, and that's going to be 0.3085, so it actually comes out to the same thing. But there you go. So we're usually, when you're doing the standard normal, we're going to use the calculator because we cannot integrate there's no way to integrate by hand the probability density function, which is this guy, e to the x squared. Basically, we cannot, there's no way to do this by hand. There's no way to do that by hand. And just because we move it over and translate it won't change this anything at all. And this is just some constant number, so this can't be done by hand. We have to use estimates, which we will learn when we get to the options. But there you go. See you guys.